That roof is on fire. Oh, we gonna take it high.
Good evening, everyone. Can you all see my screen?
Yes.
Okay, welcome to our second session this semester, and my name is still Shata. I didn't change it. I'm going to go through the objectives of our last session, and one of our objectives was to find the electric charge and how is it conserved. So we showed that it is conserved and it is quantized, meaning that we cannot create charge from nothing. If there's a charge, then that charge is the resultant of other charges, or there's actually a point charge at that place. And if you have more than one charge and they differ in signs, you can add them and you'll find the net charge. So that charge is conserved. And 1 coulomb of charge is the unit of charge, and it was quantized from the charge of an electron. There's an amount of electrons, I forgot the number, that scientists came up with, and they said when we have this much of electrons, we are going to say that's 1 coulomb. And that number, I just recall, it is something that has to do with 1 over the charge of an electron, which is, no one will ask you this. It is just to emphasize why they call it, why we say charge is quantized. And yeah, this amount of electrons, like if you have this amount of electrons, they will be equal to 1 coulomb. So that's where the coulomb is from. And now we are saying a charge of an electron is 1.6 by 10 to the power negative 19 coulombs. We also used Coulomb's law to calculate electric force between charges. This is where we were, in fact. This is where we were. We were calculating electric force between charges. So yeah. Okay, before I move to the next slide, I believe in our session today we'll be able to distinguish between electric force and electric field, calculate the field and the field due to the collection of charges, how to use electric field lines and interpret them, and maybe calculate electric dipoles and their properties. So as our first example, we did this problem and it was between two alpha particles. So those charges are the same, they are both positive, and when they are both positive they repel. That force of repulsion between them, we calculate it using Coulomb's law, and this is the electric force that we found. So in fact, in this problem we even did what? Compare the force of attraction of the gravitational attraction with the electric attraction, the electric force, and we found that electric force is significantly larger than the force of gravity, and that's why we are going to just ignore gravity in most cases. As you can see, this is to the power negative 28, this is to the power negative 63. It is so much larger than it. And then we did this problem which is between two opposite charges. So this one was the force of attraction, because now they are attracting the opposite charges, and we use the same idea that these two charges have the same amount, the same magnitude of electric force. They just differ in direction. This is where Newton's first law comes in handy. So as you can see, between these two, this charge 2 is attracting charge 1, and that force, because it is towards the positive x direction, we will call it a positive, and then F1 is also pulling F2 towards it. So this is F1 pulling 2, this is F2 pulling 1. I hope that is clear. So this is the magnitude we found. And then the last problem, okay, that's not the last, but one of the problems was to calculate the electric force between more than one charge. In fact, more than two charges. So charge 1 and charge 2 were both exerting some force on charge 3. And then that's where we had to use the vectors to find to find the electric force. So what we did was to use the formula which sums up the charges and their distances from the point charge we are looking at, which is charge Q3 in this case. The attraction between, in fact, not the attraction, the repulsion from Q1 and the attraction from Q2 when they are combined. So we realize that this method wants you to be extra careful in comparison to calculating those forces one by one, calculating the force of 1 on 3 and the force of 2 on 3 and then adding them afterwards. We still found the same value. We then moved on to this problem 21.4, which was longer because now we had to use Pythagorean theorem to find the distance between our charges Q2 and the big Q3. And we also did this problem by calculating it one by one, by first calculating the force of 2 on Q3 and the force of Q1 on Q3, and then adding our forces. We added our forces component wise, the x component with the x component, the y component with the y component. And we found that in doing so, we had to find what we call the distance between these two forces, these 2 point charges. And the distance, we did it in this point form. We said we have a point 1, which was one of our charges. We can say this is point 1 with coordinates 0, negative 0.3, and the second point charge, which is at 0.4, 0, and then finding the vector. So to find the vector, we said the vector from P1 to P2, it is just R, and we are going to subtract these two, 0.4 from 0, and in so doing, you are taking the final point and subtracting the initial point from it, not the initial from the final from the initial, to find the vector of interest. And then after finding the vector, you find the unit vector. And remember, the unit vector says take the full vector divided by its magnitude. And we said we find the magnitude by Pythagoras, whereby we add the square of our components and then taking the square root. Are we together so far?
Yes, sir.
Alright, then after that we added our components. We realized that the y components cancelled. And you are going to have to sometimes be able to just see with your eyes that some components are going to cancel. For example, you see this vector F23. If you were to compose it, this is 23, F23. If you were to compose it, this would be your x component, this would be your y component. And then if you were to compose F13, you can see it's downwards. So you see the y components cancel. The y components cancel because they are in opposite direction. The x components add because they are facing the same direction. I hope that is clear. I will just leave it here, F1 on 3. So in our session today, we are going to move on and then define the electric field. So we say this electric field, we define it by saying it is the force on 1 coulomb. You see in here we just calculated this force. But on this side, we are saying how much of this force is exerted on 1 coulomb of charge. That force on 1 coulomb of charge is our electric field. So at this stage, you are supposed to be able to now tell us how does electric force and electric field differ. They differ by the essence that electric field is the electric force on a unit charge. That's why you divide by this charge, the test charge. Now let's move on. I think I taught this stuff. If there are some arrows here, this means I taught this stuff. So what we did here was to say, okay, this big force, this big charge here is going to exert some force on this smaller charge we call the test charge. And that force, because that force can be exerted on 1 coulomb of charge, we call that the electric field. So if this charge has many coulombs, that means there will be more electric field on it, right? More charge, more field exerted. So this is when we have the positive charge and our electric field is also positive. So when is our electric field positive? It is positive when it is from positive to negative. From positive to negative. We are going to draw the field lines, the electric field lines, and we'll find that the electric field lines are from positive and they are into the negative. Into the negative. If we had another charge here, a bigger charge, but now negative, the field lines will be into that field, into it, right? And then from here, another case is whereby the same positive electric field is now exerted on a negative test charge. So that's why we realize now the force exerted will be in the opposite direction to the electric field, because now what happens is when it's negative, remember we said our electric field is from positive to negative. The electric field that this big charge Q creates is from positive to negative, positive to negative, positive to negative. So if it's a positive test charge, it will be repelled from the positive and then move to the negative. That's why the force of the electric force on a positive test charge is in the direction of the electric field. But if your test charge was negative, it is now repelled by the negative charge on the left, on the right, and towards the left. It's attracted towards the left. That's why now the force of attraction or the electric force is negative, or it is in the opposite direction to the electric field, because now it is repelled. Are there any questions so far? Hello guys. Are you all good?
Yes, sir.
All right. So let's move on. Now, these diagrams are going to show us something. Whenever we have the source of our electric field and the test charge, there is a vector. There's a vector that combines these two, connects these two, and that vector is the vector r, the distance between the electric field source and the test charge, or the point whereby we test the electric field. So it is not always the case that you will have a test charge. Sometimes we will just say, what is the electric field here? And there's no charge here. Why? We don't really need this charge. This charge is just to find the force on this charge. We can find the electric field without a test charge. Let's see. We say the force is K, Q1 and 2 over R squared. And then we said the electric field is that force over the test charge. So somewhere here we can say one of these charges is a test charge. Alright, and then if you are going to divide by the test charge, that means this test charge doesn't affect our electric field. Our electric field is independent of the test charge because we are dividing by it. So that is to say you are cancelling it. You are cancelling it. You are cancelling it. So you see, our electric field doesn't depend on the test charge. It just depends on the source and the distance away from the source. So the further you go away from the source, the weaker the field becomes. Right? So in this case, let's see. In this case, our source is positive. So you see the electric field on our test charge, or at the source, at the point where we test the charge, is away from that point. But if our source is negative, it is towards our source. We just said that in the last slide, so it is just the repetition. Now this is the formula. So as you can see, for the electric force, the Coulomb's law, we had two charges, but because we divide by one of the charges, our formula now just have one charge. So we can move on. So this diagram just shows us that we can have more than one point whereby we test our electric field, and at each point the electric field is radial and it is radially away from that source, or from that point. But if our source of electric field is negative, all the charges in space are towards it. All of them are towards it, everywhere in space. So let's do some example. Now, example 21.5. Who is responsible for this one?
It's me, sir.
Okay. May you help us reading it, and so that we can start with it.
Okay, so example 21.5. What is the magnitude of the electric field E at a field point 2.0 meter from a point charge Q equals to 4.0 nanocoulomb?
So what does the electric field formula say? Because that's what we are looking for.
E is equal to 1 over 4 pi E0.
Yeah.
Q over R squared times Q over R squared.
Q over R squared.
Yes.
So what do we have? Do we have everything here?
Yes, we have everything.
So we have the charge, we have the R squared. All that we have to do is to substitute. Alright. So that's going to be 1 over 4 pi
into 8.85 times 10 to the power negative
5
12
times 10 to the power negative 12 multiplied by
4 times 10 to the power negative 9
4 times 10 to the power negative 9 over
squared.
2 squared.
The answer is 9 newtons per coulomb.
Newtons per coulomb. Alright. That's all.
Yes.
Okay. So this is the magnitude. Yeah. This is the magnitude. It's not in vector form. Now, are there any questions on this one? If there are no questions, I would like to comment on this epsilon naught, that it's called epsilon naught or epsilon 0, the permittivity of free space. And I said in our next chapters we're going to find that we have epsilon naught. The naught just means that it is in vacuum or in air. If it is in another body, let's say the permittivity of a sponge, you'll find that it is just epsilon. Or the permittivity of a rock, something, a permittivity of something other than air or vacuum, it will just be epsilon. They call it epsilon. Alright, let's move on. Now 21.6, who's responsible for this one?
It's me again, sir.
Alright, so what? Okay, you can continue reading it.
A point charge Q is equal to negative 8 nanocoulomb is located at the origin. Find the electric field vector at a point at the field point x is equal to 1.2 meters and y is equal to negative 1.6 meters.
So what do we do in order to find it?
We first find R using Pythagoras theorem.
Okay. So that's going to be something like, okay, it's negative, so my diagram is wrong. One of the components is negative. So that's downwards, right?
Yes.
Okay. And then after doing that, okay, we have negative 1.6 and then positive 1.2. So that's somewhere here. And then we need to find this R. So we're going to use Pythagoras. So that's going to be x squared plus y squared, which is gonna be what?
It's 1.2 squared plus negative 1.6 squared.
Yes, which is
2 meters.
2 meters.
Yes, and then we must find a unit vector.
Okay, now we need to find a unit vector. So before we move on, I just want to say something. This is where we want to calculate the charge, right? That means the electric field here. Let's see, our test charge is negative. So that means our electric field here, where is it pointing? It's pointing this way, right? Towards this point charge. So this is our E field. Alright. Now we can move on. You said you're going to find the unit vector. So the unit vector, what's the formula?
It's R vector divided by magnitude.
R over the magnitude. And our R is?
It's 1.2 divided by 2.
Divided by 2.
In the x direction.
In the x.
And then it's negative 1.6.
1.6, negative 1.6.
Divided by 2.
Let me just do this. Negative 1.6 divided by 2 j hat.
Yes.
Alright. And then, okay, we can just simplify and then find that our R hat is equal to 0.6 I hat minus 0.8 j hat, right?
Yes.
Okay.
And then we go to the formula.
Or maybe before we go to the formula, in my last session, I took a long route on how to find this R vector. I took a long route because it was confusing for me. So what I did was to say this is 0.1 and it is 0, 0, and then this is 0.2, which is 1.2, negative 1.6. This is how I did it. And then after doing this, this is 0.2, right? We said our R vector. Before we find the unit vector, we need to have the R vector. And we say that's going to be 0.2 minus 0.1, which is going to be 1.2 negative 1.6 minus 0, 0. And in fact, it gives us that it is 1.2 in the I hat minus 1.6 in the J hat. So this is just to satisfy my fears, just to be sure, like to see it on paper that this is happening, right? And you never know, these physics people are so stingy. I don't know why they're like that. They'll just give you less marks just because you skipped some steps. So whenever it's possible to expand some steps, expand them. Alright, so where were we? Now we can go back to the formula.
Yes, sir.
Okay, so new page. E field. Okay, yes, the formula says
It's 1 over 4 pi epsilon naught
yes,
times q over r squared.
R hat. You see in vector form, this is how you write it. Okay, and then we substitute.
Yes.
What is the Q?
It's 8 times 10 to the power negative 9.
Do we write just 8 or negative 8? I really forgot. Guys, help. 8 or negative 8?
We write the magnitude.
So that's 8 by 10 to the
Negative 9.
negative 9 all over
2 squared.
2 squared
And then multiplied by 0.6.
multiplied by 0.6
I hat. Yes.
Minus, is it 0.8?
Yes. J hat.
J hat. Alright.
So for the first one, it's 10.8 I hat.
10.8 I hat.
For the second one, it's negative 14.4.
Negative
J
14.4 J hat.
Yes.
Newton per coulomb. Yeah. Guys, do you all agree? Does our answer make sense?
Yes.
All right. Let's go back to our diagram just to check that it really makes sense. The electric field is in this direction, right? So to me, if you were to break it into components, we would have the x component moving this way and the y component moving upwards. Right? This is an electric field in the y, this is electric field in the x. Do you realize that our component of x is negative and our component of y is positive? That means we swapped something here. Our component of x is the one that's supposed to be negative and our component of y has to be positive. What did we swap? Where did we go wrong? Do we have absolute values on this Q? You need to be careful about this one. Remember when we were calculating the electric force, we really had the absolute values.
So
Yeah.
our Q was negative, but then
Okay.
I said positive.
Okay, so we don't take the absolute value when it is electric field.
Oh, okay.
So, but when it's electric force, you take the absolute value.
So,
Yeah.
in my point of view, I think we made a mistake at the vector.
At the
Because-
vector.
Yeah.
Let's see.
Isn't it that our vector starts at that electric field and it's going to the origin?
Let's see our diagram. Remember the diagram we had said it should be from the source to where you test the electric field. You see that? So it's not really whether it's from the origin or... Okay, in fact, I think what you said, you are right, but you might be swapping the understanding. Our vector, yes, is from the origin to the point. This is R. R head because it is smaller. R is everything from here to here. So to find the vector that is from here to here, we are going to subtract this one from this one. In final from initial. And our final is 1.2 negative 1.6 minus 0, 0. Do you see that? Let's do this. Sometimes you will be given position vectors. As we said in our last diagram, in our last session, when we have position vector, they are saying that the position of this charge is at the origin. So the vector associated with it at the origin, you just take its coordinates. The coordinates of our source charge R0, we can call it R0, is 0 in the I head plus 0 in the j head. This is its position vector by just taking the coordinates and converting them into components. And the position vector of where we are testing the charge is at x 1.2 and y negative 1.6. To find the vector from R0 to R, R0 to R, we are going to say that vector, I'll call this R1 so that we can say it is R1 minus R0. And you'll have 1.2 minus 0, which is 1.2 I head. And then negative 1.6 minus 0, which is going to be negative 1.6 j head.
But isn't it that when we are dealing with a negative charge, the electric fields are going towards it?
Yes, they're going towards this charge, this negative charge, which is why we have this arrow, the arrow of the electric field.
Yeah, so meaning it's the vector, shouldn't the vector move from those coordinates to the origin?
No, we have two vectors that we need to be careful of, the position vector and the electric field vector. The position vector is from the source to where you test the electric field. The electric field vector depends on whether your charge is positive or negative. If it is positive, it will move from the position where you test to the charge. If it is positive, it will move from where you test away from it. Do you see that?
Yes.
All right. Sorry, I meant to cancel this other arrow here. Is everything clear, guys? Are there any questions? None. I would like to see you guys. I would like to see you. Raise hands if there's a question. I don't know how you are shy. If there's no question, raise your hand. If there's no question, raise your hand. 6. What is your question? Six, are you here?
Maybe it's asking
Hello?
which question you need to answer.
Huh?
Hello? Yeah.
Oh.
I'm here.
Or do you have a question?
No, I don't have a question. No.
Okay, I said if you don't have a question, raise your hand. If you don't have it.
Oh, okay.
Hey guys, don't sleep. Why are you sleeping? Are you here?
Yes, sir.
Okay. Who's here? Who's not here? Neo. Wait, Neo was just answering, right? Oh, yeah, he's raising. Okay, I think you're all here. Don't sleep, guys. Don't sleep. This is very important stuff. You see, this stuff about displacement vectors and electric field vectors, you're going to deal with it for a very long time. In almost 6 topics, you'll be dealing with it, taking derivatives. So you need to be very fluent about it. Don't sleep. So let's move on. Who's responsible for 21.7? Yo, Letabo. And Letabo is not here. Is Letabo here? Yeah, I don't think he's here. So we'll just have to help each other, guys, on how to do it. So anyone volunteer to read the question? Okay, I volunteer. I don't know why you don't want to volunteer. Okay, when the terminals of a battery are connected to two parallel conducting plates, the battery is connected to them. Yes. What happens? Leaving a gap between them, there's a gap. The resulting charges on the plates produce nearly uniform electric field. There's an electric field between these two plates. On the plates, yes, and then what? If the plates are 1 centimeter apart and the battery is applying 100 volts, the field is vertically upward with the magnitude 1 by 10 to the 4. And then they're saying if there's an electron with this mass and charge and it is released from rest at the upper plate. There's an electron from the upper plate released from rest. It was resting, not moving, or moving with constant speed. What is its acceleration? So it's going to be accelerated. Why is it being accelerated, guys? Why is the electron accelerated? There's an electric field on it. Remember, that electric field causes an electric force. And if we have force, we have acceleration, right? Someone was about to answer. I apologize for not giving you a chance to. but next time be quick. So we need to find the acceleration. In order to find the acceleration, we need to find the force. So let's find the electric force. So the formula for the electric force says KQ1 Q2 over R squared. But now we don't have this many charges. We are going to have to use another formula which says KQ over R squared, which is that formula for 1 over 4 pi epsilon naught. Sorry, I apologize. I don't know what happened. I've never seen such a thing in my life. So we are going to say the electric field is equal to the electric force divided by the test charge. But now we don't want the electric field. We have the electric field, we want the electric force. So the electric force will be the test charge multiplied by the electric field. And in our case, our test charge is the electron. So the electron multiplied by the electric field. This is the formula we are going to use to find the force. So we are going to say that force will be due to our charge of an electron is 1.6 by 10 to the negative 19 multiplied by the electric field of 1 by 10 to the 4. And then can someone help us multiply this?
So I got 1.6 times 10 to the power negative 15.
15?
Yes.
Alright.
Negative 15.
Huh?
Negative 15.
Why negative?
A.
Oh, here, negative 15 here. Oh. Negative 15. Okay. Okay, I thought you were saying the answer is negative. I was confused again. Yeah, today I have so many confusions. Anyway, who volunteers to check the time when we are busy calculating, so that it won't? Yeah. So, where were we? We don't want it to terminate unprofessionally. So this is the magnitude, right? So is this force positive or negative? Is this force positive or negative? Remember we said if you have an electric field, okay, and then there's a positive charge in that electric field, the force on it is going to be positive because a positive charge moves in the direction of the electric field. Electric field is from positive to negative. So the positive charge is repelled by the positive, attracted by the negative. It moves in the direction of the electric field. So the force on it is positive. But if it is an electron, the electric field is still from the positive to the negative, but the electron is now repelled in the opposite direction to the electric field. So the force is in the opposite direction to the electric field. Now this means that if we were to write our answer as a vector, right now it is the magnitude. As a vector, you would have to put the negative. Alright, I hope this is clear. Is this clear?
Yes.
Okay, now that we have the force, we can find the acceleration. The acceleration is going to be, this is A. Acceleration is going to be equal to the force over the mass. The force is negative 1.6 by 10 to the negative 15 the mass is negative, not negative, sorry, 9.11 by 10 to the negative 31. May someone please divide it quick.
Negative 1.76 times 10
Negative
to
1.76 times 10 to the
15.
15. That's meters per second squared. Now we are done with this part. Let's move on to the B part. So the B part says what is the speed and the kinetic energy acquired after traveling 1 centimeter to the lower plate, or while traveling 1 centimeter to the lower plate. So for the speed, remember V naught, we can assume V naught because it was constant, we can assume it was 0. Now V final, that's what we are looking for. What are we given? We have the acceleration. How many stuff do we have to know for us to find any quantity in this kind of questions?
We need to know 3.
We need to know
Also
3.
given distance.
We also know the distance. Delta y is 1 centimeter. So we can work this out. So let's go and work it out. Our acceleration is negative 1.76 by 10 to the negative, or not negative but positive. Our delta y is equal to 1 centimeter, which is 0.01 meters. What else? Our V naught is 0. Our V final is, that's what we are looking for. So which formula should we use?
VF squared is equals to VI squared plus 2A delta y.
2A delta y. Okay, I forgot something. 2A delta y. Okay, let's define our axis. Are we defining our axis positive downwards or positive upwards? That is to say, when our electron is moving downwards, is it moving in the negative or in the positive?
The positive.
So we are saying downwards is positive. Alright. So downwards is positive. What are the consequences of saying downwards is positive? This means that our acceleration is actually accelerating. It's not decelerating, right? It's moving in the direction of its displacement. Alright, let's just plug in. We said the V final, that's what we are looking for. V initial is 0. 2 multiplied by, our acceleration is negative. Are we going to write it as negative or positive? Guys?
That's positive.
As positive, why?
Say.
Yeah. We are writing it as positive because it is accelerating, even though it is negative because of our vectors, because of how it is defined in terms of this force. If you are now in the world of kinematics, acceleration is positive if something is actually accelerating, right? If someone was, let's say, someone was running backwards, but they are no longer accelerating backwards. They are now getting slower and slower and trying to run forward. That means they are accelerating. The velocity is backwards, but the acceleration is forward. If you were running backwards and then you want to run forward, but you are not yet running forward, you are slowing down, you are actually accelerating. So that's what it says. So
2 minutes left.
2 minutes left. Okay, let's just do this one quick.
The answer, sure. Okay.
Yeah, the answer.
It's 5.93 times 10 to the power 6.
Times 10 to the power 6 meters per second. So we will do C when we come back. Let's just check how scary it is. How long does it take to travel this distance? Can we not do this? How many minutes?
1.
1. Yeah, I don't want to take chances. We'll do it when we come back in 5 minutes at 9:05. Enjoy your little break.